This is a short introduction about the paper Fast and Scalable Mining of Time Series Motifs with Probabilistic Guarantees, which is a joint work with Johan Kampe. The domain is that of time series, that is, time-ordered sequences of real values. If we fix a window length W, like in this example, we can select subsequences or short snippets of length W of the input time series. Furthermore, if we consider two such subsequences, we can try to superimpose them to compare how similar they are. In this case, the blue and green time subsequences are not very similar. But if we consider the blue and orange subsequences, they are indeed very, very similar. How can we compute this similarity? Usually, people resort to using the Euclidean distance to measure the similarity between subsequences. In this case, we can see subsequences as points in a W-dimensional space. In this particular example, the time series is out of an experiment recording the behavior of a particular insect. And the subsequences highlighted up here, so the blue and the orange one, do correspond to a particular feeding behavior of the insect. Therefore, it is of interest to automatically discover such subsequences from a long and new time series. This brings us to the problem we are working with, that is the problem of top K motifs, where we are given a time series T and a length W, and we want to select out of all the pairs of subsequences of length W, the K pairs with the shortest distance between the two subsequences. In this example, we are highlighting the blue A and B, orange C and D, and green E and F subsequences. And here on the right, they are ranked by their distance. So A and B have an Euclidean distance of 10.7, C and D have an Euclidean distance of 11.6, and so on and so forth. So this would be our ranking, and in this case, here we have the top 3 motifs of our time series. Our contribution in this domain is to propose Attimo, which is a randomized algorithm for discovering the exact top K motifs. And our algorithm is able to auto-tune the parameters to the data distribution while allowing to control the success probability, that is the recall of the motifs that are being returned. And our algorithm can handle very, very long time series. For instance, a time series of 1 billion values in just half an hour. The state of the art in this domain is represented by the matrix profile, which requires to find for each subsequence the nearest neighbor, and then for you can find the subsequence with the closest nearest neighbor. That would be the top motif. The algorithms implementing this approach do leverage the fact that consecutive subsequences share a lot of structure, so you can reuse a lot of computations, and you can parallelize the execution across many GPUs, and one such implementation is able to handle a billion long time series in just one day using 5 GPUs. The main issue is that it's still a quadratic algorithm in the length of the time series, meaning that to deal with long time series, you need to use a lot of computational resources. Therefore, our goal is to try to find the top motifs without computing all pairs distances. The challenges are that, as we have discussed, subsequences can be seen as vectors, but these vectors are very high dimensional. Therefore, we are under the curse of dimensionality, meaning that classic indices, geometric indices, such as the R3 or the KD3, do degrade to linear scans, and therefore are of little help in this context. Therefore, we are using another classic technique that is locality-sensitive hashing. So now we are representing subsequences as points in the space, equipped with the Euclidean distance. And the idea of locality-sensitive hashing is to randomly partition the space and then compute the distances only of the pairs falling into the same part of the partition. In particular, for the Euclidean distance, what we do is that we pick a parameter R, a positive real, and then we sample a normally distributed vector and a uniformly distributed offset that we use to randomly project each point onto the direct direction A, which is our random direction vector. And then we use the parameter R to bucket these projections into several parts. Then, as we said, we compute the distances only of the points falling into the same bucket. The locality sensitive part comes from the fact that close points, so with a distance close to 0, have a very high probability of colliding, whereas faraway points have a very low probability of colliding. This collision probability can be further controlled by concatenating several hash functions, like tau hash functions. In this case, in the example, we are concatenating two hash functions, so two random directions for the projection, and you see that we have more refined partitioning. If you look at the collision probability plot with the collision probability against the distance, you can see that using tau equals 2 leads to smaller collision probabilities than tau equals 1. This helps in pruning out faraway points, but it also lowers the recall of the approach. Therefore, you have to repeat the same procedure several times. So in each repetition, you sample a different random partitioning and you compute a different set of distances. In the plot here, you see that increasing the number of repetitions from 1 to 10 to 100, you raise again the success probability. And here we are defining success probability as the probability of seeing a collision of points at a given distance, at least one across the big L repetitions. The important point is that for a given distance d and for fixed L repetitions and tau concatenations, we can compute the probability of having seen at least once all the pairs at the distance d by just looking at the success probability plot. So, for instance, points at distance 4 after 100 repetitions with tau equals 2 have a success probability of about 0.7. This can be used to instantiate a very simple algorithm that takes as parameters the number of concatenations tau and the success parameter delta. First off, we set up a priority queue to hold the candidate motifs, and then we perform several repetitions. In each repetition, we sample tau hash function and hash all the subsequences, and then all the pairs with the same hash have their distance computed and are inserted in the priority queue. Then we consider the kth element ranked by distance in this priority queue, and dk is the distance of such element. If we have seen all the pairs at distance less than dk with probability at least 1 minus delta, and remember that this condition can be easily computed by the discussion we had before, then we return .k elements out of the priority queue. Otherwise, we simply continue with more repetitions until this stopping condition is satisfied. The problem is, how do we set tau? Because setting the wrong value, for instance, too large, might make us do too many repetitions. A value too low might entail too many distance computations. So we adopt an approach that is able to auto-tune the parameters based on the data, but we don't have time in this video to go over the details, so please see the paper for the details. The guarantees that we prove for this algorithm is that we are able to find the exact top k motifs, each with probability 1 minus delta. So for instance, for delta equals 0.1, each true motif is found with 90% probability. This means that we can control the recall of the algorithm, and we have a trade-off between the recall and the performance. The higher the recall we want, the slower the discovery process will be. As for the complexity, we will not go into the details of this formula, but there are two parts. First, there is an index construction part, which is data independent in the sense that it's proportional only to the parameters of the LSH and to the length of the time series. Whereas the query part, where we explore the index to find the motifs, has a running time proportional to the distribution of the distances between subsequences. In this sense, our algorithm is adaptive to the data distribution. We implemented our algorithm in Rust and experimented on several datasets, spanning a wide range of sizes, so from 1 million to 1 billion, and a wide range of difficulties. Here we are measuring the relative contrast, that is the ratio between the average distance between any pair of subsequences and the distance of the top kth motif. In this sense, the relative contrast is measuring how distinguished is the motif compared to the average subsequence pair. And the higher the relative contrast, the easier the dataset. So here are the running times for the task of finding the top 10 motifs for the different datasets, and we are comparing with SCAMP, which is the fastest implementation of the matrix profile. You can see that for smaller datasets, the matrix profile approach is actually faster, whereas for longer time series, our probabilistic approach is able to find the motifs, the top 10 motifs, in a much shorter time. For instance, for Seismic, we do complete in about half an hour, whereas SCAMP completes on our hardware in an estimated 1 month. In fact, our approach does scale much better in the input size. So this is the orange line of the scalability of our approach for the task of finding a planted motif in synthetic data. Whereas SCAMP, whose performance is only dependent on the length of the time series and not the distribution of its distances, has a quadratically increasing running time. So if you're interested in further details, please go and read our paper. At this address or this QR, you can find the implementation of our code, which also has a Python wrapper for easy usage. And if you do have any question, please do not hesitate to contact me at this email. Thanks for listening.